Hello everyone, today I will talk about dynamic resources management for In-Situ Techniques using MPI-Session. And first of all, come to the motivation. Sorry. So these days, thanks to the fast development of the CPUs and GPUs, HPC systems has continuously increased computational capacity. But at the same time, the I/O subsystem developed slowly, and for our HP system, it still always have limited storage capacity. When it comes to the applications who try to make full use of HPC systems, they generate a huge amount of data. And when the scientists need to analyze this data need to write or read through the I/O system to the storage. After all the simulation or other application is done, then the supercomputer or other resources read this data back and do the analysis or post-processing. With the limited speed of the I/O subsystem and the limited storage, and these data processing or data analysis is limited in frequency. However, with In-Situ technique, we can avoid this problem or we can optimize for this problem, because when we need to do the data analysis or the visualization, we do it when the data is still in the HPC system. This can help us increase the frequency to do the data processing analysis. On the other hand, these days when we have these GPU accelerated HPC applications, we tend to port everything to the GPUs, and CPU cores on GPU nodes are idle, they are doing nothing. They are also target to be used for in-situ tasks. And there are multiple ways to classify in-situ processing. And the way we use in this work is according to how the in-situ tasks interact with the original application. The first straightforward approach is called synchronous approach. It means when in-situ tasks need to be done, we stop the original application and use the same computational resources to do the in-situ task. And when the task is done, the original application resumes. The second approach is asynchronous. It means before we start the whole execution, we set aside some resources for the in-situ task. When the in-situ task should be executed, the original application sends the data to the separate resources. In this way, in-situ task and original application can be executed concurrently. The third approach is the hybrid approach. It means part of the in-situ task is executed synchronously, and the other part is asynchronously. And for these in-situ techniques, there's already research in the field. However, Visit, ParaView, and Sensi, these popular in-situ libraries or systems, focus more on in-situ visualizations. They rely a lot on VTK data format, which limit or which might not match the original application data structure. So we choose the ADIOs, which allows us to use arbitrary data structure and offer different APIs, help us to facilitate different in-situ test cases. And in this presentation, I will bring up one example done on NEC 5000, which is one CFD simulation, and is parallelized quite well, has super good, strong scalability. In our previous studies, we already proved that by choosing proper synchronous or asynchronous or hybrid approach can improve the resources usage. However, I come to one new question. For instance, when we just start the simulation, the simulated result has so much artifacts because of numerical method. It makes no sense to visualize or analyze these data. That means it's better after certain step, we start our in-situ. For the synchronous approach, it will be fine since we just use same computing resources. But for the asynchronous approach, we set aside the resources in advance. But these resources all doing nothing or doing something useless. So it would be super promising if we can start the processes or resources later, only when the in-situ tasks need to be executed. We can fulfill this with the help of MPI-Sessions. With in our work, in addition to expand resources once, we also proposed one possibility or one advanced approach allows us to ask resources multiple times so that we only ask for necessary amount. I will come to this part later. First, I will introduce a bit more in detail about MPI-Sessions and how we use these for the dynamic resources management. We use the technique called dynamic processes with P-sets. It is a generic application interface for dynamic resources. It is centered around process sets and set operations. It can interact with resource managers. To fulfill this, we have used Petra OpenMPI-X and OpenMPI. And for more information, how these libraries are modified or these libraries are cooperated, you can visit the paper listed here. Now I will give as one example how the DPP is used. So we start with two processes which are used for the original application. This time is the NEC 5000, and then we start the simulation. When the in-situ tasks need to be executed, these two processes or the process set would contact the resource manager and ask for extra resources. And when we get the extra resources, the new P set will be used as the communication or communicator for the in-situ task. And to exchange the data before the original application and in-situ task, we need this P-set3, which is the combination of the P-set1 and P-set2. Of course, we will do multiple times data transfer to fulfill multiple time in-situ tasks. This is the logic behind how we do our basic dynamic process with DPP. This is one plot to show that how the logic of the basic dynamic in-situ technique is. So we ask for resources when it's necessary, and then do the data transfer, and loop over the simulation and in-situ task and data exchange as required. But in this case, how the amount of resources, or in other words, the amount of processes we need, should be defined before we start the execution. With the test, it's possible, but it also could be the case to know this amount. We need performance model. We need extra test to generate performance model. It's not that ideal. So we come up with one advanced dynamic in-situ technique. Again, we start with only our original application, and then when the in-situ tasks need to be done, we ask for resources. But this time, instead of asking multiple nodes or multiple amount of a large amount of resources, we ask only for one node, for instance, or only one CPU. And then when we get resources, we start the in-situ task and continue the original application. When the next in-situ task, next step of the in-situ task need to be executed, we check if we check whether the previous step is already done. If it's done, we send the if it's done, then we just send the data. But if it's not done, we ask again for one more node or one more CPU. In this case, we would use smaller amount of resources, or we just need enough resources. One more reason behind this is that usually, no matter how good the program is parallelized, it is super possible. It is possible that the more processes we use, the lower parallel efficiency we would achieve. That's actually proved by our demo test. So we built up this example using the NEC 5000 simulation with in-situ image generation. We use 24 Raven nodes to do the test for the static synchronous approach. And another approach is static asynchronous approach. That means we use 18 nodes out of 24 nodes for the simulation and the rest for the image generation. With this approach, it's much faster than the synchronous approach. But as we can see from this plot, since we start the image generation only during half of a simulation, so half of the time the processors or CPUs for the image generation are waiting there and doing nothing. With our dynamic resources management, we can avoid these idle time on the CPUs, and both basic and advanced dynamic asynchronous approach takes longer than the static one. The reason behind this is for the static asynchronous approach, we didn't use directly 18 nodes. Instead, we used 3/4 of the cores within one node for the simulation and the rest for the image generation. In this way, we limit the data transfer within the node, and the bandwidth for data transfer within the node is 10 times higher than the data exchange between the nodes. So in this case, our basic dynamic asynchronous approach means that we start with 18 nodes, and then later on we add 6 nodes for the image generation. And for the advanced approach, we also start with 18 nodes, and then we add 2 times half node. So in this way, okay, maybe it takes longer, seem to be the case, it takes longer to use the dynamic asynchronous in-situ technique. But when we come to the resources usage, it can improve the resource usage. That means we measure the resource usage by calculating the node we use, the number of nodes we used, and execution time of each node. From this plot, we can see for the static synchronous approach, although there's no idle time, it takes the most resource usage. For the static asynchronous approach, there's idle time, so it takes more resources usage than the dynamic asynchronous approaches. And interesting thing here, we can observe that with advanced approach, the resource usage for image generation becomes much smaller than the basic approach. That comes from the image generation is badly parallelized. It has not poor scalability. In general, with MPI-Session DPP, we are able to combine the dynamic resource management with our in-situ technique. Our basic dynamic in-situ technique only need to add once, we need add resources once. The same, but our advanced dynamic in-situ technique can further improve the resource usage. However, now all our tests and all our design are based on one assumption. It means that is, we have infinite resources. That means without waiting, we get resources immediately. But that's something we need to discuss or further develop better strategy to make it into a real life usage. Because when we really start this dynamic resource management, we would have some resource manager who would decide, or something like the slump system that might lead to the possibility, instead of getting the resources when we ask for the resources, we need to wait, or we need to optimize, or we need to develop some other strategy when we cannot receive the resources as we asked. That's what we would like to bring today, and I'm happy to hear some questions.
Thanks a lot for this Nice to see that finally use cases for sessions. So questions on this? Yeah.
Yeah, thanks very much. I was just curious for the processing. So the image processing, you have a known footprint for that. You also have a known time, or is it possible that it's iterative and the memory footprint can grow and the time is unknown for your processing, or is it definitive? So you know exactly what you should ask for.
So in our test case is that we did experiment before, so we know. So with this asynchronous statics asynchronous method, we already did a lot of tests, so we know when it's optimal. It means the image generation and simulation would not need to wait for each other for the data exchange. It can be fulfilled in the future, maybe with the performance model, and to know what we need.
Yeah, and then I guess the follow-up question is that given that's what you've done, so you had this infinite resource model, but how do you think you address if you have to wait 17 million years for your image processing to happen? Like, what if you can't get those resources? Is the plan to try to say we keep moving, or we have to have that image?
It's first of all, this depends on who would need these images. Okay. So we have actually think about these strategies. One possible strategy is we just do the synchronous approach, which means we make it take it longer, but we get the image at the end. And it also can be possible that, okay, we know we after waiting for a certain time, okay, we cannot get resources, so we stop the simulation, restart simulation within the resources we already have, and cut aside some resources for the image generation and start the job again. That's some strategy we have think about, and we would like to develop or test with the help or with the interaction with the resources manager.
Cool, thank you.
Yep, thank you. I was hoping indeed to see your results on a job using GPUs. So I don't know if that's a work in progress, and if you can tell us a little bit about.
Yes, we would like to also try or further develop when it comes to the situation that we already have some cores working on the GPU nodes and some CPU cores has not yet started doing something, but it still need to discuss and then further develop.
I have another question. So the nodes that are doing the post-processing, I'm sorry, the cores that are doing the post-processing. So if you are doing the job in many nodes, so you I guess the cores doing the post-processing are nodes by itself. Like you apart a certain number of nodes to do the post-processing, or what you are doing is to apart some cores in each node to do the post-processing. My question is, how are you distributing the resources for the post-processing? Are you doing post-processing in every node, or it is some dedicated nodes doing that?
Yeah. So for the statics asynchronous approach, which means we set aside the resources in advance, not during runtime, where we before the runtime already know how much we need, and then we set these resources. So for instance, we have 24 nodes. On each node, we have 72 courses. We set aside 18 courses out of the 70 courses for image generation, and the rest for the simulation. So we ensure the data exchange is within the node. But for the dynamic dynamic asynchronous approach, these we start new nodes. So the simulation are on 18 nodes and image generation are on 6 nodes, which started later.
Okay, thanks.
Good. More questions? Chat. 1, 2, 3. Yeah, there.
So I'm just curious because I was doing this type of post-processing data analysis with a cosmological simulation code.
Mm-hmm.
But the image generation was the part of the processing. It was actually like identifying structures. So it's quite a complicated iterative process. And in that case, we went with just having the identification of structure being a library that gets called. And so you have to copy data and you keep MPI locality and you try to make sure that stuff that was MPI local, that was things that you're probably going to search over. So the data you're going to try to search over to identify structures is local to an MPI node, or at least as best as you can. But the memory footprint is huge. So we have issues with like doing this on the fly in sort of this dynamic sense because the memory footprint is high. But are you guys ever doing processing with like shock identification, other things that are a bit more complex where you have to iterate to a solution, you may have large memory footprints? Would that going forward, would that be part of some of the stuff you do or no?
We didn't do something with super huge memory footprint. Instead, we did something with super huge computational requirement, something like uncertainty quantification. Yeah.
Yeah, cool.
Okay, maybe one question. You mentioned you use ADIOS in this, in this workflow.
Yes.
So do you have a possibility to switch dynamically between creating new sessions and doing the post-processing versus just writing out intermediate files to the file system? Because, as you said, maybe you don't have the resources. So just delay it by putting stuff on disk and post-processing it later. Is this possible?
Yes, it is possible. And actually, that is also some strategy we're considering. But also, on the other hand, we also have to admit, although with ADIOS, we would still output too much data. So in one use cases, we would generate 100 terabytes data just for the image generation. I think it might not be that meaningful. We keep such huge amount of data, but we can also later on develop some strategy like, okay, we limited the number of data we output to the storage. And that's what we are happy and to study with.
Okay. Yeah.
Just a comment, because I've been working with ADIOS for radio astronomy data. So have you guys looked into lossy compression? So there's GPU-enabled mGuard, which can do some compression, and it's been quite useful for us, but especially if you're trying to capture the appropriately dynamically turbulent bits of the data.
Yeah. That's also one possible choice, because currently the problem is we are able to support dynamic resources management, but not that many other applications support this feature. So and it might take some time until we get sufficient or meaningful data to even just start a simulation or start some smaller or reasonable scale tests with the data management. We are working on these. We are doing cooperations, but and this paper is just a starting point for these techniques and more things. Thanks.